Hello, and welcome to my video on divisibility rules. That is, ways to determine divisibility of a given number by numbers from 0 to 12. Is 12,345 divisible by 3? You'll find out today. Let's quickly recap what division even is. Let's say you have 20 apples, and you want to distribute them evenly among 4 friends. How many apples does each friend walk away with? You can see visually that the answer is 5, that 20 apples split 4 ways is 5 apples each. This is represented as an equation of 20 divided by 4 equals 5. This is directly coupled with the fact that 5 times 4 is 20, or to say it another way, that 5 4 times is 20. The order of division matters, unlike the situation with addition and multiplication. 4 times 5, or 4 5 times, is also 20, but 4 divided by 20 means that when sharing 4 apples with your 20 friends, they'll be walking away with only 2/10 or 1/5 of an apple each. Hope you've got a knife and a steady hand. Further things to say before we dive in. We're talking about neatly dividing, that is, division with no remainders or decimal or fractional leftovers in the result. This relies on the number to be divided, the first number, being a multiple of the number it is being divided by, the second number. On the previous slide, we saw how 20 is a multiple of 4, it's 5 sets of 4 apples, so division by 4 works neatly. It's also a multiple of 2, 5, and 10, which gets results of 10, 4, and 2 respectively. It's less neat, but you can divide non-multiples. 9 is not a multiple of 2, but it does encompass 2 4 times with 1 left over. 9 divided by 2 is thus 4 1/2, or 4 remainder 1. Your 2 friends get 4 of the 9 apples each, with 1 left over that you could split into 2 pieces. And 10 is not a multiple of 3, and so 10 divided by 3 is 3 1/3, or 3 remainder 1. Your 3 friends get 3 of 10 apples each, with 1 left over that you could split into 3 pieces. We're interested in neat and tidy division, like 10 divided by 2 is 5. Your 2 friends get 5 of the 10 apples each, or 2 goes into 10 5 times. It'll help to know not just of the times tables, as division is the inverse of multiplying. 10 divided by 2 equaling 5 relies on 5 times 2 equaling 10. These aren't the only divisibility rules that exist for these numbers, but I'm favoring ones that are easy for me to understand myself and hopefully also get across to you. And finally, this is more about the potential divisibility rather than actually computing the result. Long division is another video. First up, divisibility by 0. Quick answer, don't bother trying. Formally, the mathematicians call division by 0 undefined. And in plain English, how many apples do your 0 friends each walk away with? How do you answer the question of how many pieces you get when you split something into nothing-sized pieces? Do you get infinite pieces? Don't feel bad if you can't answer the question, because calculators and computers also soil their bedsheets when asked. But it is okay to divide 0 by something. The answer is always 0, because your friends each walk away from your nothing apple with nothing, no matter how many friends you have. You can divide 0, you just can't divide by 0. Now you can see from the right side of the function 1 over x, that is 1 divided by wherever we are along the x, which goes up in value from left to right, that for x less than 1 but more than 0, the number gets bigger as your pieces get smaller, going up towards positive infinity. But we can also see that on the left side, for x greater than -1 but less than 0, the number gets bigger in the opposite direction, going down towards negative infinity. This makes for a heck of a discontinuity at 0 itself. Perhaps the answer is both positive and negative infinity at the same time? This also will work out the same way no matter what you're trying to divide by 0, for any other number you can think of. 2 over x, 3 over x, 100 over x. -1 over x will just invert the situation. Bottom line, 0 is a universally troublesome divisor and best avoided. Second stop on our itinerary, divisibility by 1. We go from impossible to trivial, from you can never to you can always, although it doesn't do much. Let's say you have 33 apples that you want to divide into one lot. Well, it's one lot of 33 apples. Any value notionally divided by 1 is simply the value you started with. Another way to look at it is that each successive number after 1, the classics like 2, 3, 4, is just one more 1. Every single gosh darned counting number, all the way up until even the count gets tired of it, is just one more 1, and so they are all neatly divisible into 1s. And the answer to how many 1s make up this number is simply that number which you're dividing in the first place. Divisibility by 2. Now we come to our first rule that's actually useful. We can take advantage of the fact that we count by tens, and 2 goes evenly into 10. 10 is 5 2s put together. So for each successive 10, no matter whether we're talking about the teens or the 2020s, the multiples of 2 always have the same final digits, 0, 2, 4, 6, or 8. These are also all the even numbers, while all the odd numbers, those not neatly divisible by 2, end in 1, 3, 5, 7, or 9. Compare this to the situation with 3, where in the first 10 it goes 0, 3, 6, 9, but between 10 and 20 it's 12, 15, 18, so the last digits are now 2, 5, and 8. So we'll need a different trick for that. And I just want to explain the bottom chart there. I've underlined the final digit for every multiple of 2, and I've also placed dots under the numbers that are hit when you count up by 2s and 3s and 4s. For example, you hit 6 when you count up by 2 3 times, or when you count up by 3 2 times, but you miss it when you count up by 4s. 12, on the other hand, you can count up to by all 3. It's 6 2s, 4 3s, and 3 4s. You could also count up by 6s, which I don't show here, and 12 is 2 of those. And next up is divisibility by 3. I'll give you the rule first, then explain how it works. All you need to do is add up the values of the digits and check if they're divisible by 3. If you can't tell right away, you can just do it again. Take 537. Is it divisible by 3? 5 plus 3 plus 7 equals 15. Well, most people know that 3 times 5 is 15, but you can also add 1 plus 5 to get 6, and that's 2 3s. Hopefully you know that one. And sure enough, 3 goes into 537 179 times. While the rule is simple to use, the way it works is a bit subtle. It also depends on 9s more so than 3s, but remember that every multiple of 9 is also a multiple of 3. As you can see below, counting up by 9s is just counting up by 3 3s at once. Take the example of 12,345, whose digits add up to 15, but let's pretend we don't know the rule yet. 12,345 is the same as 1 times 10,000, plus 2 times 1,000, plus 3 times 100, plus 4 times 10, plus 5. Fun fact, it's also the same as 1 times 9,999 plus 1, plus 2 times 999 plus 1, plus 3 times 99 plus 1, plus 4 times 9 plus 1, plus 5. And through the distributive property, your old x times y plus z together equaling x times y plus x times z, we can rewrite all of that as 1 times 9,999 plus 1 times 1 plus 2 times 999 plus 2 times 1 plus 3 times 99 plus 3 times 1 plus 4 times 9 plus 4 times 1 plus 5. And we can shove all those 9-taculars aside because we know that they are all multiples of 9. For example, 9,000 is 9 times 1,000, 900 is 9 times 100, 90 is 9 times 10, and 9 is 9 times 1. So any combination of them, including 9,999, also is. And of course, these are also going to be multiples of 3. For our purposes, we don't actually care how many times 9 goes into it all, just that it does. And since 9 goes into it, 3 also does. So we only have left to deal with all of those times on the plus 1s, followed by the 1's digit itself. 1 plus 2 plus 3 plus 4 plus 5 equals 15, which is a multiple of 3. So the whole kit and caboodle is a multiple of 3. You could even skip adding in 3s because that's a whole multiple of 3, and the same applies to any 6s and 9s you might hit at this step. Divisibility by 4. First off, every 4 is 2 2s, so if it's not even divisible by 2, you can forget about it being divisible by 4, and this goes for all other even divisors because they are also some number of 2s, so this applies to dividing by 6, 8, 10, 12, etc. Now, unlike the situation with dividing by 2, looking at the last digit isn't enough, because the last digit flips around from 0, 4, and 8 to 2 and 6 at each 10, as you can see from counting up by 4s. 0, 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, etc. 4 doesn't go evenly into 10, but it does go evenly into 100, 25 times to be exact, as seen as in how 4 25-cent quarters make $1, or as is heard on every street corner in my country, 4 caribous make a loon. This makes the cycle through each successive 100 the same, kind of like how it was for each successive 10 in the case of 2. So we only need to check the last 2 digits, everything below the hundreds, to see if those are divisible by 4. One issue with this method is that most people don't memorize their 4 times table row all the way across to 4 times 25. But you can take advantage of your knowledge of multiples of 8 after 40 and figure out the half steps in between. Take 78 for example. We know that 8 times 10 is 80, and 78 is just 2 less, so it can't be a multiple of 4, but 76 and 84 are. Now, when I was a kid, we only memorized the times tables up to 10 by 10, but my parents' generation went up to 12 by 12, and you'll probably want to know that 8 times 11 is 88, and 8 times 12 is 96. Divisibility by 5. We count by tens, and 5 goes evenly into 10, so we see the same pattern in each and every successive 10, where a multiple of 5 either ends in 0 or 5. This also makes counting by 5s quite easy. 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100, 105, 110, 115, 120, 125, 130, 135, 140, 145, 150, 155, 160, 165, 170, 175, 180, 185, 190, 195, 200, 205, 210, 215, 220, 225, 230, 235, 240, 245, 250, 255, 260, 265, 270, 275, 280, 285, 290, 295, 300, 305, 310, 315, 320, 325, 330, 335, 340, 345, 350, 355, 360, 365, 370, 375, etc. Divisibility by 6, which is literally a perfect number, but that's another video. The property we care about here is that every multiple of 6 is also a multiple of both 2 and 3, and so if it's a multiple of 2 and 3, it's a multiple of 6. To satisfy being a multiple of 2, the number has to end in 0, 2, 4, 6, or 8, or, be an even number. And as we also looked at, any multiple of 3's sum of digits will also be divisible by 3, so any even number divisible by 3 is divisible by 6. And in the table I show how every time you hit the same number when counting up by 2's or 3's, it's the same ones you hit counting up by 6's. Below that, I also work out checking if 15, 16, and 18 are divisible by 6. Divisibility by 7. This one's a little different. Here I'm going to use a method I got from Matt Parker, and if you're interested in the more general nature of divisibility rules, you can find his video linked in my video's description. The key fact is that 7 times 14 is 98, which is 2 shy of 100. So let's take the number 4,326. There are 43 hundreds in this number, and our 98s, a multiple of 7, are 2 shy on each of them. 43 times 2 is 86 ones not yet accounted for. We add that to the 26 and come out with 112. If you already happen to know that's 16 sevens, great. But since that's still pretty big, we can repeat. There is 100 in this number and we're 2 shy on it. 1 times 2 is 2 ones not yet accounted for. We add that to the 12 and come out with 14. And as most people know, 7 goes into 14 twice. And since the leftovers were a multiple of 7, the whole thing must be. So we add the value in the last 2 places to twice the rest and see if it's a multiple of 7. Rinse and repeat as needed. If this is confusing, another way to look at it is that 100 divided by 7 is 14 remainder 2, and what we're doing here is grouping all of those remainder 2's from the hundreds together and adding it to the tens and ones part to see if that ends up being a multiple of 7. If it is, we're good to go, because those remainders of 2 came from dividing the hundreds by 7. And so if putting that together with the rest ends up being a multiple of 7, the original number must be a multiple of 7. Divisibility by 8. You'll remember that 2's repeat every 10 and that 4's repeat every 100. Well, 8's repeat every 1,000. 8 goes into 1,125 times. So you only need to look at the last 3 digits, even if it's a gargantuan number. But 3 digits is still a lot. Maybe Ramanujan took his 8 times table row out to 125, but the rest of us can bring back the basic method we used for the 7's. 8 times 12 is 96, 4 shy of 100, or 100 divided by 8 is 12 with a remainder of 4. In the case of 336, we have 300s, so we multiply those by 4 to get 12. 36 plus 12 is 48, which is 6 times 8. So the whole number, whether it's 336 or 123,336 or 789,123,336, must be divisible by 8. So the rule is add the value in the last 2 places to 4 times the hundreds place and see if it's a multiple of 8. And again, we just need to worry about the number up to the hundreds place, because the cycle of counting up by 8s repeats the same way through every 1,000. And we can repeat this as much as we need. Say you want to test a number ending in 992. 9 times 4 is 36. 36 plus 92 is 128. And to test 128, that's 1 times 4. Then 4 plus 28 is 32, which is divisible by 8. So 992 is divisible by 8. Divisibility by 9. This is a reprise of 3. Simply add the digits together and check the sum's divisibility by 9 this time. For example, 93,240. 9 plus 3 plus 2 plus 4 plus 0 equals 18. Yep, divisible by 9 all right. To break it all down again, 93,240 is the same as 9 times 10,000, plus 3 times 1,000, plus 2 times 100, plus 4 times 10, plus 0. So it's also the same as 9 times 9,999 plus 1, plus 3 times 999 plus 1, plus 2 times 99 plus 1, plus 4 times 9 plus 1, plus 0. Hit up the distributive property again and redistribute as 9 times 9,999 plus 9 times 1, plus 3 times 999, plus 3 times 1, plus 2 times 99, plus 2 times 1, plus 4 times 9, plus 4 times 1, plus 0. We put aside the known to be a multiple of 9 nine-taculars, and then we just need to reckon with all of those times on the plus 1's and the 1's digit itself. 9 plus 3 plus 2 plus 4 plus 0 equals 18, which is a multiple of 9. So the whole dang thing must be a multiple of 9. In fact, you don't even have to add in any 9's at this step because they themselves are whole multiples of 9. Divisibility by 10. Well, this one is easy because we count by tens, or to speak formally, we use a decimal, base 10, number system. And 10 is the first number here that isn't representable by a single digit. It needs to be represented as 1 10 and 0 ones. 1 0. If and only if the final digit is 0, the whole number is a multiple of 10. That is, every situation where you don't have any ones left over. Compare with binary, base 2, where 2 is represented as 1 0, and in that case it's 1 2 and 0 ones. And every time the final bit is 0, the whole number must be a multiple of 2. If you'll indulge a brief digression, below I show what counting from 0 to 32 in 4 commonly used bases looks like. Base 16, hexadecimal, has to use letters A through F to denote 10 through 15, because each place has to go up to 15 instead of just 9 like in base 10. Let's look at hexadecimal 24 being represented as a 1 and an 8. 3 8s are 24, and 2 of them make up the 1 in the 16's place, with 8 left over in the 1's place. Meanwhile, in base 2, it's 1 1 0 0 0, 1 in the 16's place, 1 in the 8's place, and 0 in the 4's, 2's, and 1's places. 25 is 1 more, so the binary becomes 1 1 0 0 1, while the hexadecimal is now 1 9. Divisibility by 11. To test divisibility by 11, you can use an alternating sum method. Starting from the left, alternate between subtracting and adding each digit and see if the result is a multiple of 11. For example, 918,082. 9 minus 1 plus 8 minus 0 plus 8 minus 2 is 22, a multiple of 11. Even 22 itself, 2 minus 2 is 0, also a multiple of 11. Although 0 as a multiple of things really does play the field. Another example, 64,130. 6 minus 4 plus 1 minus 3 plus 0 equals 0, also a multiple of 11. Now let's talk about why this works. The reason this works is because there are nearby multiples of 11 to each successive power of 10. Here are the first 6, so you can see the pattern. For example, 99 is 9 11s and also 1 less than 100, and 100,001 is 9,091 11s and also 1 more than 100,000. The general proof is out of my ken, but I'll show you the algebra for the 3, 4, and 5-digit cases. Let ABC be the hundreds, tens, and ones of the number you want to check. Quick algebraic notation recap. When the numbers are cheek to jowl with the letter, it means multiply, and the value for a letter with no number just occurs once. You could say it's implicit multiplication by 1. So for a 3-digit number ABC, the A value is multiplied by 100, the B by 10, and the C by 1. Or ABC equals 100A plus 10B plus C. We can convert these powers of 10 into their nearby multiples of 11, plus or minus 1 to bring it back to their proper values as the case is for each. So that gives us 99A plus 11B minus B plus C. We can now separate out the parts that are a multiple of 11. So we have 11 times 9A plus B plus A minus B plus C. So since the left term, 11 times 9A plus B, is definitely a multiple of 11, we need only worry about the right part. Is 319 a multiple of 11? 3 minus 1 plus 9 equals 11, so it surely is. Now for 4 digits. A, B, C, D equals 1000A plus 100B plus 10C plus D. Converting the powers of 10 again gives us 1001A minus A plus 99B plus B plus 11C minus C plus D. And separating out the 11s, we get 11 times 91A plus 9B plus C minus A plus B minus C plus D. Now we could just test a 4-digit number for divisibility by 11 like that, but we can also factor out the negative sign, every number is also divisible by -1, to make the right side take the form we're used to, A minus B plus C minus D. So now we have 11 times 91A plus 9B plus C minus, altogether, A minus B plus C minus D. Don't worry that we're now subtracting all that, because as long as the resulting number is a multiple of 11, it doesn't matter whether it's going up 11 or down 11 from the left term, so we just need to check our A minus B plus C minus D. Let's test 9053. 9 minus 0 plus 5 minus 3 equals 11. Yep, definitely a multiple of 11. And here's the 5-digit breakdown. ABCDE equals 10,000A plus 1,000B plus 100C plus 10D plus E. Converting the powers of 10, we get 9,999A plus A plus 1,001B minus B plus 99C plus C plus 11D minus D plus E. Factor out the 11s for 11 times 909A plus 91B plus 9C plus D plus A minus B plus C minus D plus E. Let's test 16,918. 1 minus 6 plus 9 minus 1 plus 8 equals 11. Rock on! Divisibility by 12. At last, our 13th and final divisibility rule, at least for this video. If this video gets 1 million views, I'll produce a sequel. A number is a multiple of 12 if and only if it is a multiple of 3 and a multiple of 4. So to check for divisibility by 12, we can combine two of our earlier rules. To check the multiple of 3 property, add the digits together and check if they're divisible by 3. To check the multiple of 4 property, see if the last 2 digits are divisible by 4. Let's take 83,628. 8 plus 3 plus 6 plus 2 plus 8 equals 27. Yep, divisible by 3. And is 28 divisible by 4? It sure is, so 83,628 must be divisible by 12, and by a very nice number as it turns out. Thanks for watching. Don't forget to like, comment, subscribe, hit that bell, share the video, stay hydrated, recycle your aluminum cans where facilities exist, brush your teeth, fluff your pillows, and I'll see you in the next whatever the heck I put on this channel.